All right, so let's take a look at the energy changes involved in the vaporization process. And so since we're dealing with like heat and energy, we're going to be looking at the enthalpy of vaporization or delta H. We'll just use VAP as the abbreviation there. Remember, there's a bunch of different types of enthalpies. We've covered a lot of them in the past. We always just label them with whatever process that we're trying to figure out the energy associated with that process. And so we can define the enthalpy of vaporization as the energy required to vaporize 1 mole of a liquid at the normal boiling point. Remember that term normal means it's at 1 atmosphere of pressure. And there's a direct relationship between energy and intermolecular forces. The stronger the intermolecular force, it requires more energy to cause that vaporization, which in turn means that there will be a higher delta H of vaporization. So let's kind of jump into a problem. Let's look at the vaporization of water. So we're going to convert liquid water into water vapor, and its delta H vaporization is 40.7 kilojoules. So our problem is how much energy is required to vaporize 10 grams of water at its boiling point. Let's assume a normal boiling point. So we're starting with, the only value we're given is 10 grams of water. And you have to remember that these delta H values, these enthalpy values, are assuming 1 mole of substance. So let's get this into moles of water. 1 mole of water has a molar mass of 18.02 grams. And then the other data that we have is we know that 40.7 kilojoules is required to vaporize 1 mole. And so this is just a simple plug into your calculator, and that comes out to 22.6 kilojoules. Now, one thing I want to point out here is the sign. Notice this delta H vaporization is a positive value. What does that mean? Well, that means it's an endothermic process, which makes sense. In order to heat something up, you have to provide energy. Let's look at the opposite process real quick. Vaporization and condensation. I can't spell right now. Condensation are opposite processes, but they require the same amount of energy. So the delta H of condensation for water is the same value, but because it's an opposite process, its sign is negative. It's the opposite sign of the vaporization, which basically tells you what about condensation? It's an exothermic process, which is kind of weird because it's like, well, you're getting colder. But in order for a liquid to lose kinetic energy, well, and become a solid, it has to lose that energy. And so the condensation process results in a loss of energy. Now it's kind of we're kind of switching gears a little bit, but looking at something kind of related. And this is the use of something known as the Clausius-Clapeyron. Probably saying that wrong, but the Clausius-Clapeyron equation. And this is something that we use to describe the relationship between temperature and vapor pressure. Because as I pointed out earlier, temperature and vapor pressure are not linear, meaning if I double the temperature, I don't double the vapor pressure. It actually is a lot more than double the vapor pressure. And the formal equation for this is pressure equals some sort of constant. That constant is unique to every substance times E to the negative delta H of vaporization divided by RT. Now, this E is a mathematical function. I would get used to where that's at on your calculator. If you don't know where it's at, come talk to me because you're going to be using that quite a bit this semester and even next semester. So make sure that you're aware of that. We don't use this form of the equation a whole lot. There's one that's a lot more useful. It's called the two-point form. This is more useful because we can use 2 points of data to find an unknown. And essentially, it takes this original Clausius-Clapeyron equation and allows us to compare pressure and temperature at two sets of conditions. And you don't worry about how to derive this, but well, the natural log of P2 over P1 is equal to the delta H of vaporization divided by R, and then times this term, 1 minus T2, or I'm sorry, 1 over T2 minus 1 over T1. And as I said, this allows us to look at pressure and temperature conditions at two different settings and then find something that we don't know. We could even find the delta H of vaporization if we know pressure and temperature of the two conditions. Now, there's one thing I want to highlight here. This R is the gas constant, but it's in different units and therefore has a slightly different value than when we saw R in the gas chapter. The value of the gas constant here is 8.314 joules per mole Kelvin. That looks a little bit different than our gas constant from the gas chapter. And so its value is different. You don't have to worry about how that derivation happened. You can look in your textbook. The textbook goes through how the two values are related and converted into each other, but you don't have to worry about that. But I want to take a little bit of a rabbit trail real quick, and I want to talk about how to deal with natural logs. Okay, let's say, for example, we have some unknown, the natural log of some unknown equals a number. How do we isolate the thing inside the natural log? Well, what we do is we raise each side, make it a power of E. And again, E is a mathematical function that's on your calculator. Make sure you know how to access that and how to use it properly. But what happens is E and the natural log kind of cancel out. And so whatever was in that natural log is now no longer in it. And so if you just, maybe practice this, find the E key, try this operation, E to the fifth power, it's about a value of 148. So that's how we get rid of natural logs. You're going to have to do that in the use of this equation. So let's go to an actual problem here. So delta H vaporization for hexane, here's the formula, is 28.9 kilojoules per mole. And its normal, I'm going to underline this, and I'll tell you why in a little bit. Its normal boiling point is 68.73 degrees Celsius. What is the vapor pressure at 25.00 degrees Celsius. So notice here we have two different temperature pressure conditions, or we're changing temperature, we're seeing how it affects the pressure. So we're going to use this two-point form of the Clausius-Clapeyron equation. And so let's rewrite it down here. And it does not matter what you label as one or two, as long as you keep them the same. So if your initial conditions are going to be P1 and T1, that's fine. If you have your final conditions be P2 and T2, that's fine. Just don't mix and match them. Okay, so you'll want to, like in your mind or maybe even on the side on your paper, define what you're setting as your initial and final. So for the purposes of this problem, let's solve for P2. Okay, that's what we're going to try to find the vapor pressure at 25 degrees Celsius. So before we start defining everything, let's rearrange this equation to solve for that. Okay, so since I have a natural log and my unknown is in the natural log, I'm going to raise or use E and raise those things to the power of E. And what that does is it gets rid of the natural log. And it does kind of complicate a little bit or makes it a little messy on the right side. But all of this stuff is now an exponent. And then I'm going to get P2 by itself because that's what I want to solve for. So I'll multiply both sides by P1. Oops. All right, so there's my equation. Now let's define, let's read the problem again and define what everything is. So delta H of vaporization, problem says it is 28.9 kilojoules per mole. What I want you to do is kind of circle, highlight, star the fact that that's in units of kilojoules. I'll tell you why it's important in a little bit. Okay. And then R is our gas constant, 8.314 joules per mole Kelvin. And then let's define our temperatures here. Okay, T2 is our final temperature. And so we want that in Kelvin. It's starting out as Celsius, so I'm going to add 273.15. So that's 298.15 Kelvin. And then T1 is our normal boiling point. So the 68.73, and I'm going to convert that to Kelvin as well. And that is 341.88 Kelvin. Now here's where things get a little weird. If we're solving for P2, we have to know what P1 is. We can't have an equation with two unknowns. How do we know what the initial pressure is? Well, this is why I had you underline the word normal at the beginning. What is the pressure for a normal boiling point? The pressure is 1 atmosphere. So that's what I'm going to put there. And then we could just solve for P2. Okay, so one thing before we get going is that I want to address again the units thing. So notice we have units of kilojoules here, but units of joules here. So doesn't matter which one you decide to convert, but just do convert one of them to the other. So what I'm going to do is I'm going to convert this R value to 0.008314 joules per mole Kelvin. All right, so let's plug all of this in. So our delta H vaporization, we're getting the negative sign there. So negative, and then we have 28.9 divided by our R value, 0.008314. And then time, we have 1 over T2 minus 1 over T1. And all of that is 1 atmosphere. One of the most common mistakes, an easy mistake to make on this is not necessarily you don't know how or where the numbers are coming from. It's just you're not putting them correctly in your calculator. So I highly encourage you to go through this problem. I'm not going to go through every mathematical operation, but if you put this into your calculator correctly, you should come out to 0.225 atmospheres. All right, so as I said, go through this, make sure that you know how to use the E function on your calculator and that you know where all of these numbers are coming from and how to put them into the equation. And you should be able to take this two-point form of the Clausius-Clapeyron equation and solve for any, excuse me, any term in there, whether it's pressure, temperature, or even the delta H of vaporization.